Hi there everybody, Mr. Newland here. I wanted to try to find the safe speed a car could go around a curve, a banked curve, so that it doesn't end up sliding up and off the plane. So I'm going to draw here this vector going away from us into the page, indicating the speed direction, the direction of the motion and the direction of the velocity. So the trick with banked curve problems is to try and figure out which piece you're looking for and which pieces you know and which pieces you can eliminate. And here we're looking for the maximum safe speed so that the car can go around this curve without sliding up and off. So let's draw the forces acting on the car. We've got mg down, we've got normal up like that, and we've got friction acting this way. And I'm going to tell you why I drew it down the plane instead of up the plane. If this car goes any faster, I'm saying that its tendency is going to want to slide that way. By the way, the radius of curvature of this curve is pointing off in that direction. So that actually helps us out. That means we can call this plus x, since that's the direction of the centripetal acceleration, and plus y will leave like we normally do, which makes good sense to me. And let's do some components on these. So if this guy's theta down here, then that's theta there for the normal. If I take the normal force and break it into its x and y components with the system I've drawn, that angle that I've swept out there, that one's theta. And then we're going to do something similar with friction. So let's label them so it'll be easier to write them down. The guy on top up here is opposite the angle, so that's n sine theta. The guy, so that's in the x direction. In the y direction, we've got n cosine theta. For friction, the one that's parallel is f cosine theta, and this one off to the side is f sine of theta. So friction is mu times normal, by the way. So let's do this. Let's try to figure out the safe speed using Newton's second law. So the sum of the forces in the x, that is a big sigma. In the x direction, it's mv squared over r, because that's where the axis of the plane of rotation is. The road is forcing us to move in a circle. So the sum of the forces in the x is mv squared over r. And then we've got, pointing in the same direction as the acceleration, in sine, based on what I've labeled up there, and f cosine, and they're acting the same direction, so they're positive. And then let's see if I can make my next sigma maybe not quite as crazy. The sum of the forces in the y is 0. That's the point of this maximum safe speed. If I go any faster, the sum of the forces in the y is not 0. And we've got n cosine up, so that's positive. And f sine is down, so that's negative. And mg is down. And then I'm going to verify that I've, based on all the things that I've drawn here, I've got normal acting in the x, friction acting in the x. I've got normal acting in the y, friction acting in the y. And then weight is also acting in the y direction. Okay. Remember what I said a minute ago, we're trying to eliminate something, and we can first of all replace the friction variable with the expression mu times normal, and then we can end up eliminating the normal vector altogether. So let's see if that'll work. So mv squared over r, where v is that safe speed we're talking about. By the way, mass is a constant, the radius is a constant, theta is going to be a constant, mu will be a constant. So the only thing that's an unknown here is the speed. So mv squared over r equals n sine theta plus, and I'm going to replace friction with mu times normal cosine of theta, which means I can factor the normal out of this and get sine of theta plus mu cosine of theta, and that equals mv squared over r. And that's equation 1. So let's do this something similar with the sum of the forces in the y. Let's move the mg over to the left-hand side. So take this and move to the left-hand side. mg equals, and I'm going to go ahead and replace friction with mu times normal, so n cosine minus n mu n sine of theta. And we're going to factor out the n here. And we get cosine of theta minus mu sine of theta. That's a theta, and that equals mg. And this is equation 2. And in both cases, what I'm going to do is solve for normal. So the first thing I'm going to do is I'm going to move this expression over to that side, and then I'm going to move this expression over to that side. So let's see if I can do that without messing it up. So mv squared over r times 1 over sine of theta plus mu cosine of theta. That's not too bad. And do the same thing with equation 2. mg times 1 over cosine of theta minus mu sine of theta. Hang on, my parenthesis got a little ahead of me there, didn't it? There. So notice that the masses actually drop out of the expression for the safe speed. The mass of the car doesn't determine the maximum safe speed. Interesting to note. And then I'm going to solve v squared over r equals, I'm going to solve this expression for v, g times, and I'm going to multiply both sides by this quantity. So I got sine of theta plus mu cosine of theta over cosine of theta minus mu sine of theta. And all of that times g. And note, by the way, that this expression here is the centripetal acceleration, v squared over r. So that might be helpful. Or it might be useful in some other circumstance. There might be some way that was useful in the question asked, but not here. So I'm going to multiply the top and bottom by 1 over cosine of theta for it doesn't seem like it's helpful, but when I did the derivation for the safe speed before, we got square root of rg tan theta, and I don't see a tangent in here, but I can get one in there. So v squared over r equals g times, and I'm gonna distribute this 1 over cosine divided by 1 over cosine, and the top becomes tangent of theta plus mu, and 1 minus on the top, and 1 minus mu tangent of theta, which means v equals square root of r times g times quantity tangent of theta plus mu over 1 minus mu tangent of theta. So I multiplied both sides by r, I took the square root, and I put in the tangent form, which isn't necessary to plugging in, like you could have gone to this step up here and plugged in numbers into your calculator. I just wanted to show you that there is a tangent form for the safe speed before you slide up the plane that's similar at least to the safe speed if there were no friction at all, like that equation 2 right there. So we ended up with a similar kind of expression. Good.